6.2 is about addition and subtraction and estimation. It's still within the rational numbers. So we're talking about, the majority of this section anyway, about adding and subtracting fractions, okay? Adding and subtracting fractions is without a doubt a more difficult concept for kids than multiplication and division. Do you remember why? It's okay. Yeah, there's this common denominator issue, right? I think several of your heads nodding. We don't have to do that with multiplication and division at all. And so this addition and subtraction has this extra sort of feature on the front of it that makes it a little bit complicated. The other thing that makes it complicated is that when we do add things, we don't add denominators together. And that can also be confusing for kids. And pictures will help with that, and I'll show you how. But this idea of being able to multiply is really simple because you just multiply straight across. I mean, that's great. And actually, division is quite similar because it turns into multiplication in most cases. But the addition and subtraction can be very daunting to students. So let's talk about adding and subtracting first with like denominators. So this is sort of what we were getting at. When we have a like denominator, so in this case I've got the letter B down here, and we have these numerators, we add the numerators together, but the denominator stays the same. The best argument that I have, that is to say, that I've used before with, you're looking at about 4th and 5th grade students for this content. They do start looking at fractions a little earlier, just not doing quite this detailed of addition and subtraction, but is to think about this in terms of a picture. I don't know exactly why I chose to draw rectangles. Circles would work as well, but I've got rectangles right now, so we're going to go with that. And we can actually talk about adding the numbers like 1 over 4 plus 2 over 4 together. And I recognize that 2 over 4 does not, it isn't in a reduced form. It's not a problem for what we're working at right now. So the problem is that if I do 1 over 4, where'd my line go? No. We're going to take our image and we're going to split it into 4 equal boxes, and we're going to shade in one of them. Okay, so that's 1/4, and then we don't even necessarily need the second image because the denominators are the same. I was thinking about doing the second picture for you in a minute, and then I'm supposed to add 2/4. So because each of these boxes are size 1/4 or 1/4, we can actually talk about taking and adding 2 more together. So this is actually 3 boxes shaded in of equal size 1/4. So we have 3/4 in terms of the picture. Now if you have different denominators, you do need to have a like denominator before you can actually combine them. So there's several ways to get a like denominator. One way is to get the least common denominator. Another way is to get a common denominator. And there's a couple of sort of visuals that you can go with. The visual that your book is showing you is not one that, it's not hard, but it's not the one that I learned growing up. But I think it's really good, especially for people who have that sort of a picture in their mind of how they do things as a visual picture. I had a brother-in-law who, the code on his, like, alarm on his house or whatever, he didn't really know the numbers. He knew the pattern of what he pushed. That's just how he pictured it when he would put it in. This kind of has that feel to it. So if we have, and I'll write it a little bit bigger, if we have A over B plus C over D, what you can actually do is you can multiply these two together, the first diagonal, kind of like when we cross multiply. So AD. You multiply the second diagonal together, so then plus BC or CB. And then you multiply the bottoms together, BD. And it just has a very nice feel to the multiplication. So that works well. The drawback in doing that is it does get you the common denominator, which might not be the least common denominator. So for example, if I used the same fractions that I used earlier, but I used them in their reduced form, and I had 1/4 plus 1/2, and I do this, I'm going to multiply across one diagonal. That's going to give me 2. I'm going to multiply across the other diagonal. That's going to give me 4. Draw my line, and then I'm going to multiply the denominators together, which is going to give me 8, which is correct. There's nothing incorrect about it. But the problem is that my answer ends up being something that I have to reduce. So it's just something to be aware of, is that because of sort of the simple or the ease of doing that to begin with, you're going to end up with simplifying at the end. And it's the reason that you end up with simplifying is simply because you found a common denominator instead of a least common denominator. So we would be 3 over 4, just like we had before. So another option is to simply look at the numbers that you're given. So I had the numbers 1 over 4 and 1 over 2, and to actually kind of compare these two. So if you compare 2 and 4 and you kind of ask yourself, is there anything that I can multiply one or both of them by to get the same number? And you want to use the smallest thing possible. And with these numbers, they're small enough that hopefully you recognize that if I had multiplied the 2 times 2, I'd get 4. And so you would multiply this 2 by 2, and anything you do to the denominator, you have to do to the numerator. And that idea of doing things on top and bottom is also sometimes causes a little bit of concern for students that just don't remember to do it more than anything else. And or maybe even recognize why they're doing it. So this is then, of course, still going to give you 3 over 4. One other nuance that I might point out is that this right here is not the same as saying I'm taking the second fraction. I sometimes will have students do this. And I recognize what you're telling me. You're telling me you want to multiply the top and the bottom by 2, but that's really not mathematically what that says. That says I'm multiplying by 2. And the number 2 is the number 2 over 1. So if you're multiplying, you need, both end top and bottom by 2, which we were in this problem. You need to make sure that you're right, that you're multiplying each of them separately by the number 2. Does that make sense? Okay, I think I have an example or two. All right, so the first one, 1/3 plus 5/3 is 6/3. Fantastic. They had the same denominator. And do we get to stop? No, not yet. What is 6/3? 2. So what could you do to show, why is 6/3 2? What did you actually do to say that? Yeah, you actually divided, right? You looked at what in the world is 6 divided by 3. So recognizing that this idea of fractions was really just an idea of division, or at least that's one way to use it. All right, the second one does not have the same denominator. So you can choose least common denominator. You can choose this sort of cross-multiplying smiley face thing going on. Or you can simply multiply them out differently, however you'd like to do. So go ahead and do that one, and then we'll make sure everybody has the same answer. Okay, so I use that sort of picture method that I showed you on the other page. I get 23 over 12. Unless it tells me to, I'm going to leave it like that. That's the way this book is doing that. The curriculum that my daughter's using right now always wants them to turn it into mixed numbers, which is fine too. You just have to recognize what your curriculum is telling you to do. So our book just goes ahead and leaves it the way it was. If you notice, this particular part of the problem started out in an improper fraction anyway, 5 over 3. So leaving that answer as an improper fraction makes as much sense as anything else. So we have 23 over 12. All right, now we're going to actually talk about mixed numbers. Mixed numbers are very practical in everyday life. They are less practical to actually work with mathematically. It's just the reality. So for instance, used in everyday life, we would talk about eating 2½ cookies. If anybody told you I ate 5/2 cookies, you'd probably go like, what? I mean, we don't talk like that, right? But of course, 2½ and 5/2 is the same quantity. It's the same number. If I ate 5 halves of cookies, they were all split into halves, and I ate 5 of them, I would have eaten 2½ cookies. So we're going to talk about changing a mixed number, changing a number into a mixed number, and then changing a number into an improper fraction. So we'll do the mixed number one first, example number 3. So you guys mentioned this earlier. That fraction bar actually means division, right? So when we see 14 and we see the fraction underneath having a 3 in the denominator, we really are asking to divide 14 by the number 3. So 3 goes into 14 how many times? 4 times. 4 times 3 is 12, and then 14 minus 12 is 2. So the way we report our answer is that the number on top is the whole number part. The remainder on bottom is the 2. It's the numerator of my fraction. It's what's left over. And then this number 3 on the outside, which was the original divisor, is still the divisor. It doesn't move. So 14/3 is the same thing as 4 2/3. Example number 4, first of all, notice it's negative. So I'm going to put the negative on when I'm done. I'm going to manipulate with it without that first because I don't need it to be manipulated. It's not going to change anything. So we're going to take this number 3 5/8. And I'm going to show you visually how you change it, and then I'm going to talk to you about why it works, because it looks a little bit like magic. I mean, it really does. So the way visually that I talk about doing this is that we're going to take the 8 and the 3 and we're going to multiply. And then we're going to kind of keep going around. We're going around the circle, if you will, clockwise. And then you're going to add that to what the value is on top. So 8 times 3 is 24. And then 24 plus my 5 is 29. And then we're going to write that 29 over the original 8 that we started with. 29 over 8. I mean, that's a quick and easy, and it's negative because I started off with a negative number. That's a quick and easy sort of algorithm that is a way to do something that always works, and it works very well. It's very efficient. I'd like to show you why it works because, again, it does look a little bit like magic. The number 3 is the same as the number 3 over 1. Agreed? So when we actually write 3 5/8, we're talking about 3 plus 5/8. It's like having 3 whole pizzas and 5/8 more of a pizza. So this is 3 plus 5 over 8. So what we're doing really when we work this problem is we're getting a common denominator. The denominator that we're getting here is the denominator 8 because the original first 3 has a denominator of 1. So when I multiply the 3 times the 8 right here, it's because I'm actually taking and getting a common denominator for the 3. I mean, that's what's really happening. So 3 times 8, the 24 is where that comes from, and then I'm adding it because it's adding fractions to that fraction's numerator, the other piece of the fraction, which is in the numerator, the 5. So that's why that's working there for you.
I think I remember you did the multiple, like there was negative 3, and then you times by 8, you had negative 4, but you need to add 5.
Yes. Yes, and that's a very good point, Shelby, which is why I leave the negative off until the end. So are you guys following what she's saying about the negative? I mean, it kind of feels like you would be multiplying the 8 times the negative 3, and if you're not careful, then what you're going to recognize is then, or you're going to think is that you've got negative 24 and positive 5. What you really have is negative 24 and negative 5 because the whole thing is negative, which means both pieces are, which you could also deal with from that perspective if you want to think about it that way. I just choose to take a look at it and say, hey, look, the answer is negative at the beginning, so the answer is going to be negative at the end. I mean, not the answer, but the number. So, any questions on this?
Can I make a comment?
Yeah.
Over J term, I observed in my fifth grade math class, and they're actually not teaching this way anymore.
What are they doing?
In California, they're doing Common Core, and so it's all like picture stuff. And so they take like 3 holes and they'll divide it into pies and stuff like that. It's really interesting.
And I have worked with a curriculum, and it predates Common Core stuff, but up in Ohio that did a lot with those kinds of things too. And those are great tools for understanding, but there comes a point too, I think, when we don't want to draw a picture to do the same operation over and again. So I think I'm a big fan of pictures because I'm a visual person myself. And so please do use those with your students so that they can start to understand the connection between them. I think that's a great thing to do.
It was really interesting because I was watching her teach it, and I was like, I learned it that way. So.
Yeah. Yeah. All right. What do we have next? Let's see. All right. Additive inverse property. All right. For any rational number a over b, there exists a opposite of it, negative a over b, in such a way that a over b plus negative a over b is 0. We saw this with integers. For those of you who took Math 1, some of you last semester even. Any number has an opposite number to it, including the number 0. What's the opposite of the number 0? 0, it's itself. It's okay. You can be your own opposite. It's all right. 0 has an additive inverse as well. It's just himself. That's fine. I mean, and May feel a little bit awkward to put a negative in front of it because it's really not needed, but it's fine. You can call it that. I mean, 0 minus 0 is 0. That's fine. So an additive inverse is just, and it's unique. It does talk about that too. It's a unique number that makes this work. All right, the additive property, addition property of equality says that if you have two numbers that are equal and you add something to both of them, they're still going to be equal. And that's all it says. So if I have the numbers a over b and c over d and they're equal, they may even not look the same, right? 1 over 2 and 2 over 4. They don't look the same, but they're the same number. Then if I add something to one of them and add the same number to the other one, they're going to stay the same as they were before. This is the idea. I like to use this example that if I have lots of sister-in-laws, and all in my husband's side of the family, they're all taller than me, and in my side of the family, they're all shorter than me. But if we all stood up here and then we all put on 2-inch heels, we'd still all be the same height apart as we were originally. Okay, you take all of us, and you could do this in the classroom too, of course. You take everyone in the room, we stand all barefooted, and then we stand all in a 2-inch heel. Well, the 2-inch heel didn't do anything in terms of making us a difference in height. Our difference in height stays the same as what they were before. Okay? It's kind of what happens when I weigh luggage too. I step on the scale with the luggage, because I want to figure out how much the luggage weighs, but you can't put the luggage on the scale itself. Does anybody else do this? When you go flying now, especially? And so you weigh yourself, and then you weigh the luggage, and then you know the difference because of that for the same reason. All right, both of these are properties we use extensively when solving equations. I mean, these are important concepts. Your kids are not going to probably be solving equations until you hit about 6th grade. It's where you usually see equations start coming forward. I will say that the curriculum they're using in my daughter's school, they did a little bit in 5th grade with it. And so it's definitely moved its way down a little bit more than it was. I think the first time I did it was in 7th grade, actually. But it's come down a little bit ways of where it was before. But talking about these properties when you encounter these kinds of numbers doesn't have anything to do really with solving equations. It's a property. It's a true fact about it, right? I don't need to make the apple pie to know that apples, have certain properties and there are features about an apple kind of thing. All right, so what we're going to do, though, in this section is we are going to take a look at solving some of these. And the reason we are is because your certification goes up to 8th grade. And you definitely solve equations in 7th and 8th grade. So it's good to be aware of some of this. And I want to show you a couple other things as well. I can't remember if I do it in this one or if it's the next one. I'll do it on this one first. There's at least 2 ways to solve this problem, and I want you to be aware of both of them. And in part because I don't know what your curriculum is going to show you, but also in part because no matter what the curriculum shows you, if you have a kid and that's just not working for them, you have another tool in your tool belt to be able to say, and even if you don't remember, you have a way to go look it up to find it out, another way for them to do the problem. So here are our numbers. We have our equation. We have x minus 2 and 1/2 equals 3 and 1/3. All right, so what we're going to do for the first way is I'm going to call it, well, let me actually pause here. The first step that we're going to do in solving this equation is what? There is really only one step. Yeah, we're going to move the other value, right? We're going to add the 2.5 to the other side. Okay, and the property that we're using when we do that is we're using the additive property of equality. I mean, that's why we're allowed to do that anyway. The thing I wanted to show you, though, comes after that. So the issue has to do with adding the numbers 3 and 1/3 and 2 and 1/2. There are 2 approaches to doing that. I will tell you, I only learned one of them when I was in elementary school, and so that's fine. And it's not the one that I prefer now at all. So I'll teach you the one that I learned first, and we'll just kind of take a survey when we're done, and you can tell me which one you guys have done the most or learned the most or whatever. The way that I was taught was to do it with improper fractions. So what that means is that you take both the numbers you were given and you turn them into improper fractions. So I have 3 and 1/3, so if I'm turning this into an improper fraction, I do 3 times 3 plus 1, and so that gives me 10 over 3. And then I'll do 2 and 1/2, so I do 2 times 2 plus 1, which would give me 5 over 2. Perfect. Now these are not terribly large numbers. They aren't terribly, either the numerators or the denominators, they really aren't terribly big. So this works fine to do it this way. And it's not a good example, I guess, to tell you why I don't like this method. We'll come across a better example later. But what we need to do now is we have two fractions that have different denominators that I'm supposed to add together. So what do we need to do? Yeah, either do that multiplication business or get a common denominator. Somehow we've got to add these with a common denominator together. So simply because I've shown this to you already, I'm going to do it this way. I've got 2 times 10, so that's 20. I've got 5 times 3, so that's 15. And then my denominator is 6. So 20 plus 15 is 35, and then over 6. And now this is a good example where in the end I need to change it back into a mixed number. Why? The problem started out with mixed numbers, so the answer will be in mixed numbers as well. So at the very end I have to do the division, 35 divided by 6. How many times does 35 go into 6? 5 times. 5 times 6 is with a remainder of 5. So this is 5 and 5 6. This is improper fractions. There are two things I don't like about them. Again, this is not a great example for showing you why. But the one thing I don't like about them is I do end up with a numerator that's kind of large, or at least has the potential to be. I mean, 35 in a numerator is getting up there. If the mixed numbers had had a larger whole number part to them, they would get up there much quicker. I mean, we'd have a lot bigger numbers really quickly. The second thing that I don't like about this is at the end, I still have to do another step with this division. And I might even have to do a step with reducing because I got the way I got my common denominators. So it feels like there's a lot of steps. So let me show you another option. And it's not going to hurt my feelings if you like that option. That's fine. You can like that one best if that's what you're comfortable with. As long as you learn both of them, I'm good with that. The next approach is the mixed number approach. So the way this one works is that we have the same values, 2 1/2 plus 3 1/3. Or reversed. I don't know why I put them in the other order this time. But what we do is we add the whole number parts together, and we add the fractional parts together in separate quantities. We add them together separately. So if I add the whole number parts together, what is 2 plus 3? 5. And then I'm going to add the fractional parts together, but they don't have the same denominator, so for right now I'm just going to write them separately. Okay? All right. I like the fact on this one that my fractions that I'm actually dealing with as fractions are a little bit smaller. I think that's kind of friendly. 1/2, 1/3. I also have small numerators with those numbers. So when I work with these numbers and get common denominators, I'm not going to get a crazy large, fractional exponent or numerator. All right, so I'll do it the same way I did before, just for consistency for now. So I have 1 times 3, which is 3, plus 2 times 1, which is 2, over 2 times 3, which is 6. And so in the end, I end up with 5/6 with my original 5. So I have 5 and 5/6. And I think there's about 2 steps less. There is a nuance to this with subtraction that's a little bit messier, and I'll show you that when we get to that one. But this is another approach. So I'm just curious, who learned the first one, improper fractions? Okay, who learned mixed numbers? A few of you did because I saw you looking at me. Okay, so we're about 2/3, 1/3. That's very interesting. All right, so let's do another property. Let's do things with some subtraction now. Subtraction, if a over b and c over d are rational numbers and we want to subtract a over b minus c over d, it's the unique value e over f such that when you add it to the c over d, you get back a over b. And I'm just going to use some whole numbers to tell you that this works because it works the same way whether I use whole numbers or whether I use fractions. All this is saying is that the reason that 5 minus 2 is 3 is because 5 is equal to 2 plus 3. It's the piece that 2 is missing to equal 5. That's all that's saying. Okay? So it's defining subtraction in terms of addition, which is oftentimes how it's taught to begin with anyway. How do I know what 5 minus 2 is? Well, you start at 2 and you count up to 5. What's missing? I'm missing 3 numbers, that kind of a thing. All right, if I have rational numbers a over b and c over d and I subtract them, it's the same as adding a negative, which you guys have been working with that idea for quite some time now, of course. So addition of a negative and subtraction are the same idea. All right, so when we subtract fractions, If they have the same denominator, we do just like we did with addition. We just subtract across the top. Denominator stays the same. We can do a picture arguing that same thing. You know, you can take, for instance, if I had 5 over 6 minus 2 over 6, I can draw, and I'll do a circle this time. I can draw a pizza. I can make it have 6 pieces. I can talk about the fact that I brought the pizza home from the party and it had 6 pieces. Originally, you know, when it was purchased, but it had 5 when I brought it home. Right, so there's my 5 pieces of it, and then I eat 2 more of them. So originally this one's gone, now this one's gone, now that one's gone. So now I have 3 pieces of pizza left out of the original pizza. And then we can reduce that to being half, and you can see that from the picture, and that works fine. Same thing with different denominators. We can still do the same kind of a cross multiplying around. Makes it look like a smiley face, right? So we can still do that if you'd like. The subtraction sign stays in the middle, whereas the addition sign stayed in the middle with the addition problem. It's not any different. Okay, so let me take a look with you at another mixed number problem that involves some addition and some subtraction. Martine bought 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8 yards, pants using 2 3/8 yard, and a vest using 1 2/3 yard. And the question is how much fabric will be left over. And this is a very typical 5th grade question. And so you'll see this written in a very much this way. There's a couple of ways, and I don't mean like the last example I did, but there's a couple of ways to just set the problem up to begin with. So when you see this problem, what do you think you would do first? You could do that. So you could start with the 8 3/4, and that's literally what you would do if you were making these outfits, right? You'd roll out the fabric on the floor, and you'd cut off the piece that you'd need, in essence subtracting it off, and you'd cut off the second piece you'd need. So you could subtract them off one at a time. Someone else, what's another thing you could do?
You just add the ones that you're going to subtract off.
You could add all the ones that you're going to subtract off, because what we really want to know is simply the piece that's left over. That's going to be a little bit quicker because we'll have fewer steps to do, I think. So let's go with that route. So what we're going to do is we are eventually going to take this away from 8 3/4, but the first thing we're going to do is we're going to add the 1 7/8, the 2 3/8, and the 1 2/3 together. Now, it looked like about 2/3 of you were quite comfortable, or at least had been taught the improper fraction approach. And I do want to show you the nuance of what happens with the mixed number approach here so that you're aware of it, because there is a little bit of an awkward thing that will happen. So I'm going to show you the mixed number approach to this one, and we'll go with that for this particular problem. So we're working inside the parentheses right now. We'll do the subtraction part in a minute, but I want to work inside the parentheses right now. You'll notice that I've got 1 + 2 + 1. That's what? 4. All right, so I've got, I'll still write down my 8 3/4. Eventually we'll get to that piece of it, but right now I've got 4. I can also add these fractions together without any extra work right now. 7/8 and 3/8. Yeah, 10/8. And I've got the 2/3. So I've got 4 + 10/8 + 2/3. Oops. All right, so tell me some of the weird things that are already happening in my problem. There's at least 2 of them. I already have an improper fraction in the middle of it. What else? Denominators are different. And then there's one more thing. We'll fix that in a minute. That's not something that's weird for this particular one right now.
The numbers will be big.
Yeah, if we do it from here, they will be big. Something else I was thinking of. You guys come up with good stuff. The 10 and the 8 right now are something we can simplify. Yeah, we didn't have that happen before. So let's deal with the improper fraction thing first, because Rachel saw that one first. The 10 over the 8 can be simplified to what? Right, so before we simplified, though, that's not what I meant. Let me try to clarify. It can be changed into a mixed number as what? Like made not improper. I want to turn it to something not improper.
Oh, 1 2/8.
All right, good. So we can use division, right? If we actually would divide 10 divided by 8, we would find out that this is 1 and 2/8. So I've got 4 plus 1 plus 2 over 8 plus 2 over 3, and there's nothing special about the fact that I chose to change that first. I could have done the reducing first. I'm going to do both. So, all right, so I've got 8 3/4 minus 5, and then, like you said, we can reduce then. So what's the 2 over 8 reduced to? That's 1 over 4 plus 2 over 3. All righty. So what am I going to do with the 1/4 and the 2/3? Okay, we can do that. And it's not really cross multiply. I know we kind of keep saying that because cross multiply is something we do across equal signs. But we're going to get a common denominator is what we're really doing when we do that process. So we have 1 times 3 is 3, plus 2 times 4 is 8, over 4 times 3, which is 12. So I have 8 3/4 minus 5 and what? 11/12. And we haven't actually done a subtraction one yet, but can you see a potential problem? Yep, that is my problem. So what we'd like to do is we'd like to take whole number minus whole number, fraction minus fraction. And I actually saw this set up, and this is the first time I've done this in class this way, but I thought it was really helpful when I saw it set up this way, so I'm going to show you guys this setup. A lot of students learn to subtract by stacking things. Did you do that? Where they're stacked on top of each other? The reason I'm going to show you this is because I liked the idea of what happens. Let's say, for instance, you had 112, let's say, minus 39. What do you have to do, or at least sort of the one that you were default programmed to do when you were in about 2nd grade? You did borrowing, right? And so you looked at the number 2 and you said it's not big enough. So you took this 1 and you turned it into a 0, hence you borrowed 10 and you added it to the 2 to give you 12, right? You can do that with fractions as well. You can borrow. Now, before I borrow these fractions, we need a common denominator. The 3 over 4 and the 11 over 12, in order to combine them, they're going to have a common denominator anyway. So, okay, there's a fly. Let's take the 3 over 4. What would I need to do to change 3 over 4 into having a denominator of 12? Great. All right, so over here, I would end up with 9 over 12, right? Okay, so just like with whole numbers, I can't take 11 over 12 away from 9 over 12. I need to borrow. So I'm going to borrow. I'm going to turn the 8 into a 7. That's fine. So, you know, in essence, you went over to your neighbor's house who had 8 pizzas and you borrowed a pizza. I mean, you're not really giving it back, but, you know, you borrowed it. You borrowed a pizza, but the pizza needs to be split into 12 pieces. Okay? You still have 9 over 12. You have 9 pieces of a pizza at your house already. You take their 12 pieces of pizza, so how many pieces of pizza do you have? You add them, right? So what did you get? 21? That's right. Okay? So what we really did is when we borrowed it, we borrowed 12 over 12 because that's equal to the number 1. Why do we want to borrow 12 over 12? Because we've got a 9 over 12 to combine it with. We're borrowing a whole pizza, which is equal to 12 pieces. So then the 12 plus the 9 would be the 21. Okay? And this is exactly what the curriculum was actually showing in my daughter's book when I saw the kids doing it, just so that you know. And it mirrors something we did really well in Math 1 when we were working in other bases. Do you remember borrowing in other bases? Some of you were like saying, I thought I was going to get to forget that. She brought it back up. Man. I mean, it mimics that very same thing. I mean, and you can think this one actually in terms of inches really well, too. You took 1 foot and you turned it into inches. Well, that's 12 inches, and 12 inches plus 9 inches would be 21 inches. So, all right, so let's do the subtraction now because we're set to do it. We can do it in either order because we've actually got things that are above, values that are above, that are bigger than the value below that we're subtracting. We'll start on the right-hand side since that's kind of the default normally. I have 21 over 12 minus 11 over 12. What does that give me? 10 over 12, very good. And I have 7 minus 5. What does that give me? 2. So this gives me 2 and 5/6. I know some of you are thinking, man, that was really kind of complicated. There's a lot of steps in that. I promise you, if you do with improper fractions, there's also a lot of steps because there's just a lot of numbers here for one. The other thing that you encounter is you encounter numbers that are actually quite large because you have denominators of 8, you've got whole numbers of 8, and the numbers get quite big. So I have it written down both ways on here, so just so you know, I've got a 210 out of 24. Okay? Because if you get flat out common denominators between 4, 8, and 3, that's 24. That's a big number to be working with. So there's good and there's bad. I'm not saying you have to like one or the other, but just recognize that fact. Yes, Bridget?
So what if on the last step here at the bottom, we took it and turned it into improper fractions and had the common denominator of 12? Would we still get 2 and 5/6?
Mm-hmm. Yep, you would. Definitely. Oh, and I should have put, I'm sorry, I left it off because I was so excited about all the numbers. This is yards, right? It's yards of fabric. Yes?
Is it okay to switch like that in the middle? Because we kind of started off using the mixed number one and then we switch it to improper fractions.
Mhm.
Is it okay as long as we end with the mixed number?
Yes, yes. And the only reason we switched to improper fraction here is so that we could do the subtraction. Yeah. We had to because we didn't have enough to subtract from what we already had before.
Right, I was just
Mhm.
meaning, like, it's what Bridget was saying at the bottom.
Mm-hmm.
Like, I would want to do that too. And
Yeah.
I just didn't know if that was.
You can, that's fine. Mm-hmm. Sure. All right, ideas of being less than, greater than, and we're doing a little bit of approximation, a couple slides on this here at the end. Definitions of less than and greater than. A over B is less than C over D. If when you take C over D and you take away A over B, it's a positive number. And I know we don't always think of it that way, but the reason, for example, that 5 is less than 7 is because when you take 7 and you subtract 5, you have leftover. This is bigger than 0. There's more of it on the right-hand side. And C over D is greater than A over B if and only if A over B is less than C over D. All that's saying is that I can switch the order of the numbers around, so 7 and 5, as long as I switch the order of the sign around as well. Right? The sign switches when the numbers switch. Estimation, convenient fractions. Convenient fractions are fractions that are approximately or roughly equal to what we started with. Sometimes some of the problems that you're given, they tell you, it's almost like multiple choice. Which one is the closest approximation? And they give you like 0, 1/4, 1/2, 2, 3/4, and 1. And they're just saying which one are you closest to because they're more convenient to use. So these are some examples of convenient fractions. Of course, they're not all the convenient fractions that exist. 1 over 10 is not an inconvenient fraction, for example. So if you're taking like 1/2, 1/3, 1/4, 1/5, 2/3, 3/4, there's lots of numbers that we think of more conveniently than others. Okay, so that's kind of what that's getting at. This one says estimate the following fractions, and then it says is your estimate high or low? Oops. So 12 over 82, for example, is about what? Do you know? Like think about these kind of numbers up here, convenient numbers to switch them to. It's about 1/4. I think maybe about 1/8. Do you think? 1/8 or 1/7, something like that? 1/4 is a little bit big. One of the ways to think about this is that if you are sort of looking at approximations, 12 is almost 10 and 82 is almost 80. So that's like 1 over 8, if you divide them both by 10. So this is approximately 1 over 8. I'm not too concerned because this section's not trying to get into this detailed. When it's asking you, is it a little bit high or a little bit low, you're welcome to use a decimal approximation just to check and see which one it is on the problem. This particular one is a low estimate, apparently. It's a lot easier to determine that on part B. But what this is basically just saying is that is this number smaller or bigger than the number I started with? It's a little bit smaller. But that's what that's telling me. The second number right here, 2 over 1001. I mean, first of all, it's almost 0. Let's just be real about it. It's almost 0. But if we wanted to keep it as a fraction, what's a simpler fraction approximately that it's equal to? 1 over 500. Oops, I didn't mean to put equals. And what did you really do to get 1 over 500? Yeah, you just sort of ignore the fact that that's 1001 on bottom and you treat it like it's 1000. I mean, it didn't change very much, right? So, oops. So you're sort of treating this like it says 2 over 1000. Now, I can tell you, since I made the denominator smaller in my approximation, what that did is it made this a high estimate. I made my fraction a little bit bigger because I divided by something a little bit smaller. So that one's a fairly easy one to make that claim about. All right, one last slide and we're done with this one. You guys ready? Okay. Write a story problem. I know that a lot of your curriculums that you're going to be using will come with pre-made tests and things like that, and those are fine to use. But occasionally, there's going to be a problem that is going to look something like this for a kid. I don't know what they're going to be doing with it, but they're going to be looking at you and they're going to say, but when would I ever have to subtract those numbers in real life? It happens, and sometimes the answer is, well, you really wouldn't, right? I mean, I get that too. But it's not a bad practice to get into, to be thinking of, how does this really make sense? Why, in real life would it ever be used? And these are not terrible numbers to use. So what kinds of reasons might you want to subtract 5 1/4 minus 2 1/3? What's a context where you might actually have those kinds of numbers and subtract them? Any thoughts? Distances would be a good example, right? It's 5 1/4 miles between my house and Joey's house. And I've ridden my bike 2 1/3 mile. How far do I have to go? That would be an example, right? What else? Cooking measurements is a good example as well. So especially if you're working with kids who like to cook, and that doesn't necessarily mean a girl versus a boy. But yeah, you could talk about having 5 1/4 cup of sugar or flour, take your pick. And the recipe calls for 2 1/3. So how much flour is left over when you're done? How much do you still have to work with for the next recipe, kind of thing? Those are the two that I usually hear. Does anybody come up with a different one? Excellent. We'll call it done then. All right. All right. So we have the homework set and the group work set right here then.